I just
Okay. Maybe we could just get started then.
Right.
So hi. I think a few of you know me already, but I'm not David Elishoff. I'm supposed to give this lecture today. Unfortunately, he got called away to a last-minute engagement. My name is Ram, and I work as a statistical consultant in Dr. Elishoff's consulting group. And today we're going to be talking about multiple hypothesis testing, also known as the multiple comparisons problem. I have a tendency to talk quietly, so if my voice starts trailing off, just let me know and I'll try to speak up a little bit. So we're going to start with just sort of a review of hypothesis testing in a single case. Then we'll talk a little bit about the reproducibility crisis and the relationship between these things, and then we'll go into sort of multiple testing and different concepts of it and how to sort of address it. So with hypothesis testing, we're typically starting out with some sort of a general scientific hypothesis. For example, that the expression of some gene is elevated in, say, lung cancer patients. And while that sort of is often kind of adequate for scientific purposes, to do a sort of statistical assessment, we typically need to make it more specific. So we might say that the mean expression is higher in cancer versus control patients, or maybe the median expression is higher. And it's important to realize these are not the same thing. So we could have a gene where the mean expression is higher, but the median isn't, and vice versa. So right there already, from the translation from a scientific hypothesis to a statistical hypothesis, we're already making some choices and that we could potentially make differently. And then once we've decided on one, so let's say we're planning to compare the mean expression, we want to sample patients from our study population and then use what we call hypothesis testing in order to evaluate this statistical hypothesis, which we take to be sort of a translation of our underlying scientific hypothesis. So the analytical framework for hypothesis testing is that we sort of pose a null and an alternative hypothesis. And usually what we mean by the null is sort of that in the population, there's really no difference. So if we're talking about mean expression levels, what we're saying is that in the population of patients, the mean expression of this gene is about the same in cancer patients versus control patients. And the alternative is stipulating that there is a difference. So the mean expression levels are not the same in cancer and control patients. And it's important to understand this is a statement about the population, not about the sample that's in front of us. There's pretty much always some difference in your sample. It's a question about, can we use the sample to sort of infer something about whether there's a population difference or not. And the way we do such a test is we sort of suppose that the null is true, sort of playing devil's advocate, and we compute a test statistic. And the test statistic is usually some measure of how discrepant the data is from the null hypothesis. So if our null hypothesis is that the mean expression level is the same in both groups, then a reasonable test statistic might be the mean difference in the sample between the two groups. And that's a good measure because the bigger that is, the more sort of discordant our data is with what the null hypothesis would sort of lead us to expect. And generally, if the test statistic is sufficiently extreme, meaning it's very discordant with the null hypothesis, then we, on the basis of that, reject the null in favor of the alternative. And scientifically, the sort of translation is that we're concluding that the data is sort of supporting our scientific hypothesis in some sense. On the other hand, if it doesn't take on a particularly extreme value, we say that we fail to reject the null. And that means that the data don't necessarily support our scientific hypothesis. And this is sort of an important distinction because we're not typically sort of saying that the data is consistent with the null or supports the null, because we usually don't think the null is actually true. The null is sort of like a devil's advocate. It's sort of saying, if there were no difference at all in the population and what we're observing in the sample is entirely spurious, would we see the kind of differences in the sample just by chance? And so we're not saying that that means that it is true, the null, just that our data is not strong enough to allow us to reject the null. And so that's the general way in which we sort of approach hypothesis testing. And when we do this, there's sort of two types of errors that we can make. The null hypothesis could be true, or the alternative hypothesis could be true, and we could either reject the null or fail to reject the null. And so this gives us sort of four combinations of scenarios And if we fail to reject the null is true, that means we've basically got the right conclusion. So that's sort of a success. And similarly, if the alternative is true and we reject the null, that's also a success. But if the null is true and we reject the null, we call that a type 1 error. And a more illuminating name would be sort of a false positive, that we sort of think we found something, but in fact, there's nothing to be found. And on the other hand, if the alternative is true and we fail to reject the null, we call that a type 2 error or a false negative, meaning something actually is there to be found, but we didn't find it. And in general, we don't know the truth about the population because we never see the population. We only see samples of it. So we don't know whether the null or the alternative is really true. However, because there's these two types of errors that we can make, what we can do is try to control the probability of each type of error. And if we can keep those low, then we can sort of say that our test is a sort of a good discriminator between the null and the alternative. And the type 1 error rate is really just the probability that we reject the null when the null is true. And we call that alpha, and that's sort of often referred to as the significance level of the test. And the type 2 error rate is the probability that we fail to reject the null when the alternative is true. And that's called beta. And usually we refer to 1 minus beta instead of beta, and 1 minus beta is the power of the test, which is really the probability that we do reject the null when the alternative is true. And so these are sort of two parameters that kind of characterize the quality of the test in terms of how well it's able to correctly reject the null when the null is false, and fail to reject the null when the null is actually true. Now, when we think about type 1 and type 2 errors, in general, there's sort of a trade-off between the two. If we have a fixed study design and we try to lower the type 1 error rate of our test, we tend to increase the type 2 error rate and vice versa. And so, we have to make some sort of decision about this trade-off, and we have to do that on the basis of things like costs of the different types of errors, as well as maybe what you sort of subjectively think based on your prior information about which, is the null or the alternative more plausible. And generally, it's hard to get sort of agreement on these things across different settings. And so what we often do is we instead present the p-value, which is sort of a way of being agnostic about this trade-off. The p-value sort of tells you what's the minimum significance level at which you do, in fact, reject the null. And the nice thing about that is that you're not taking a stand on what is an appropriate type 1 or type 2 error rate. You're just saying, this basically tells me for any given type 1 error rate whether I do or do not reject. And that allows the sort of audience of your research to sort of decide for themselves, okay, maybe I think 0.05 is a reasonable type 1 error rate, or maybe I think that's too aggressive, maybe we should use 0.1 or 0.01, whatever the case may be, and then they can assess for themselves by sort of looking at the p-value. And so that's sort of why p-values kind of play the role that they play, is they sort of allow us to be sort of agnostic about this trade-off, which we think depends on things that are sort of hard to pin down and agree on. And this is sort of a visualization of the trade-off I was mentioning. The two distributions that you're seeing are sort of the distribution of the test statistic under a scenario where the null is actually true versus some particular scenario where the alternative is true. And so even if there's no difference, the observed difference in the sample could be anything from a very negative difference to a very positive difference. And if there is some true positive difference, there's also a range associated with that, though you're more likely to see large positive differences and less likely to see large negative differences. And that's kind of what those two distributions represent. And that line there that says sort of any mean is kind of our cutoff for deciding, okay, we're going to decide in favor of the alternative or we're going to decide in favor of the null. And what you can see there is that on the right-hand side is the type 1 error, because it's, under the null, we've decided to favor the alternative, which is an error, and that's sort of the red region there. Whereas under the alternative, if we've decided to, favor the null, that's a type 2 error, what's on the green side there. And so as you move that line, you sort of increase, if you move it to the right, you increase the type 2 error rate and reduce the type 1 error rate. If you move it to the left, you reduce the type 2 error rate, but you increase the type 1 error rate. So this is sort of the trade-off that I'm talking about, and this is sort of what a p-value sort of allows you to be kind of agnostic about. So that's sort of the way to think about, testing a single hypothesis. And this is sort of the way that I think a lot of research has been done for a long time. And starting maybe around 10, 15 years ago, there started being some general concerns about some of the output of this type of research. And probably the most sort of famous paper on this that sort of started a lot of this discussion was this paper by Ioannidis called "Why Most Published Research Findings Are False." And this wasn't actually an empirical study where he sort of looked at actual papers and said what's going on. He just made sort of a theoretical argument that, because people are doing lots of multiple testing, their type 1 error rates might be higher than they are, or people are sort of overly optimistic in the effect sizes they might see, and so their power is actually less than they think it is, or maybe they're testing implausible hypotheses to begin with, and so there's a greater chance of a false discovery. So he sort of made this argument that the way in which this sort of hypothesis testing framework is being used can frequently lead to a situation where we're sort of claiming that we found something, but in fact, there's nothing really there to be found. And so this paper generated a lot of discussion, and where that I think eventually led was to an interest in sort of evaluating the reproducibility of a lot of fields. And the most famous sort of example of this was in psychology, particularly in social psychology, where this group called sort of they were sort of trying to estimate the reproducibility of psychological science, where they sort of took a sample of papers from top psychology journals and tried to replicate them and see, to what extent they found results sort of concordant with what the original study found. And I think what people were surprised by is that the rate of replication was really low. That they only found something like a third of the studies which were significant the first time around were significant the second time around. And that seems sort of surprising because if you think about type 1 error rates of the usual 0.05 level, power of 80%, for example, what people are usually aspiring to, it seems a little weird that you'd end up with a situation where only about a third of these studies are actually replicating. Now, what's interesting about this is that it did turn out that the studies that reported smaller p-values to begin with actually tended to replicate better. So it does seem that the p-value is actually sort of tracking the reproducibility of the result. When you have a smaller p-value, it does have a greater tendency to reproduce. But reading a p-value by itself can sometimes be misleading as to the actual error rate that you should expect. But it may still have some value as sort of an ordinal measure in terms of lower is better. So after this study came out, there was a lot of hand-wringing in the statistics community because there was a lot of people sort of saying, is the problem with reproducibility that people are misusing p-values? And the ASA, the American Statistical Association, issued this statement about 3 or 4 years ago, and basically it sort of tried to clarify a lot of misconceptions about p-values, and more or less sort of restated what I covered in the first few slides here, but sort of tried to avoid a lot of common misconceptions that people have about p-values. Misconceptions that I think, the common view is that they may have led to a situation where people sort of expected error rates to be better than they actually are. And this was sort of, this generated a lot of debate because they were trying to construct a consensus statement where they would get a large number of statisticians of diverse opinions to agree, and that's sort of hard. And so it ended up being a fairly limited statement, but generated sort of a large literature of responses of people offering more detailed views on this. One particular direction some people took, and this actually, Ioannidis was part of this group, was to say, okay, well, maybe the problem isn't p-values per se, but it's sort of the 0.05 cutoff that we usually use. And so this group basically proposed kind of lowering the threshold to 0.005, with the idea, again, that sort of smaller p-values are better from a reproducibility standpoint. And if we're unhappy with the reproducibility rate we're getting with the current p less than 0.05 threshold, then perhaps we'll get a more satisfactory reproducibility rate by lowering it to 0.005. The response to this from a lot of people was 0.05 is completely arbitrary and 0.005 is just as arbitrary. And, we could get a situation where lots of promising but sort of underpowered studies sort of end up getting thrown out because you're setting such a hard, threshold to meet. But on the other hand, there's sort of this benefit of, losing a lot of what are probably false positive studies. A different view is that the whole issue or the whole notion of statistical significance is really the problem, that we shouldn't be interpreting things like p-values dichotomously as you either have significance or you don't. or you either reject the null or you don't. You should just try to treat p-value and other sort of measures as sort of numerical measures that sort of quantify the strength of the evidence, for or against a null hypothesis. And this paper actually was published in Nature just like a month ago, and generated some 800 signatures from a mostly sort of partisan group within the statistical community. So it's not clear that it's representative of a general viewpoint, but there's clearly sort of a lot of active debate about this issue. And yet another thought, and I think this is probably the most popular view at this point, is that the real problem is not p-values or statistical significance, but what's called p-hacking, which is sort of a combination of practices where you sort of try to manipulate your data and the way you do your analysis to get a p-value that's less than whatever the arbitrary threshold is, in this case 0.05. And so this cartoon gives sort of a nice illustration where the researchers initially sort of hypothesized that jelly beans cause acne, and they didn't support their conclusion. They got a p greater than 0.05, but then some brilliant person on the research team said, well, it's maybe not all jelly beans, it's maybe only jelly beans of a particular color. And so they looked at, purple jelly beans and brown jelly beans and gray jelly beans and pink jelly beans, and none of them were significant until they got to green, which is over in this top right panel here, where they suddenly discovered that for green jelly beans it was significant. And so then they go and they publish a paper, and the media reports it as green jelly beans linked to acne with 95% confidence. Now the problem here is that they did 20 different colors, and if you have a type 1 error rate of 0.05, which is essentially 1 over 20, then what you would expect is that one of these tests would be significant just by chance, even if there's absolutely nothing going on. So what they did is they just discovered that sort of chance significance, and then wrote their report up as though that was the only thing that they ever looked at. So that's sort of what p-hacking is sort of the idea of trying out lots of different things to try to get a small p-value, but then not accurately sort of reporting the process that led to it, so that the p-value appears to take on a greater sort of meaning than it actually has. And an even more general concern is this sort of general issue of using the data to decide what type of analysis you do. So in the previous example, what these people did is they literally went and tested every single color to see which one was significant. But an interesting point is that you don't actually have to do that. All you have to do is have a scientific hypothesis that's vague enough that allows you to test potentially many things, and you have the same problem. And so that's what this paper by Gelman is about, is sort of, if your scientific hypothesis is there's some color of jelly bean that causes acne, then even if you only actually test one thing and it just happens that you tested green, that could just be as spurious as, as trying out all those different tests. And the reason is basically because you chose green based on what you saw in the data. So you only did one test, but you looked at your summary statistics, for example, and you noticed that the green one looked kind of different. And so then you went and you did your one test and you said, look, I only calculated one p-value, so everything's fine. But in fact, the problem is exactly the same because the scientific hypothesis was too vague, and so was consistent with too many distinct statistical hypotheses. So I don't have a resolution to this. I have some strong opinions on this, but I'll save those for another time. But this is sort of a really active issue now, and I think because this is a class about sort of high throughput analysis, where sort of multiple testing issues are really central. It's important to sort of think about this larger discussion that's going on in the research community about this, because there's a feeling that sort of carelessly using p-values at a minimum is sort of a bad research practice and is leading to unreproducible research. And so there's, it's going to become, I think, increasingly important when trying to publish your research to sort of actively think about how you can sort of improve on just calculating p-values to try to control your error rates. And just as an example of how this debate is sort of continuing, we now have some journals, for example, this political analysis journal, which tried to ban p-values, and sort of people coming back and saying, well, you're saying p-values don't provide support of a model, but does anything provide support of a model? And I think that's a fair question. And this journal actually ended up walking that back and re-allowed p-values after lots of debate about this. So there's a feeling that p-values by themselves are not really living up to their potential that a textbook would sort of lead you to believe, like what I would have led you to believe based on those early slides. but there's sort of a, continues to be a debate about what the best way is to try to improve on that. So let's talk about now testing multiple hypotheses, and this is sort of, I think, one major sort of source of concern when it comes to sort of lack of reproducibility, and the sort of p-hacking example was a clear case of this. So in our original example, we were just testing whether one gene might be differentially expressed between cancer and control patients, but suppose that instead of one, we have n genes, and n could be some really large number, like 10,000 or 100,000. Now, if you perform M hypothesis tests, even if your p-value succeeds in controlling the error rate for a particular gene, when you add it all up together, the overall error rate of the panel of genes is going to be pretty high. And multiple comparisons corrections are basically just techniques that you can use to adjust either the significance level or the p-value that you get from each test in order to control this sort of aggregated error rate. And in the literature, there's many different concepts of these aggregate error rates, but the two sort of most popular ones that you'll tend to see are sort of what's called the family-wise error rate, or FWER, and the false discovery rate, or FDR. So we'll talk about those in the sequence. So the family-wise error rate is just the probability that we make even one type 1 error, meaning if the null is true for all of our m genes, what's the probability that for one gene or more genes, we conclude that there's actually a difference when there isn't. So one way to think about how this is affected by multiple testing is to think about sort of flipping a coin. So when you flip a single coin, if you ask what's the probability that you get one or more heads, you could think of that as the opposite of getting all tails, right? One or more heads means you didn't get all tails. And since we only flipped once, that's just 1 minus 0.5, which is just 0.5. If you make it 2 flips, so now again, it's the opposite of getting all tails, but now 2 tails is 0.5 times 0.5 is 0.25, and not getting that is 1 minus, which gives you 0.75. And with 3 flips, it expands in the same way and becomes 0.875. So what's happening is that as we're doing more coin flips, the chances that we get at least 1 heads out of that is steadily rising. So similarly, what's happening with multiple testing is that we have some error rate, say 0.05, but it's like we're repeatedly flipping a coin. And the chances that any one of our flips is going to be, erroneous is going to be compounding in this way. And so you can start out with a test level error rate of 0.05, but end up with a panel level error rate or a group level error rate of something much higher than that. And the family-wise error rate is just one sort of concept of that. So there's this inequality from probability theory, which I won't try to demonstrate or anything, but it turns out that the family-wise error rate is really just never going to be more than the number of genes you're testing or the number of tests you're performing times the significance level of each test. It could be less than that, but it's never going to be more than that. And so if we wanted to use this to protect our family-wise error rate, we don't want it to go more than alpha star, then a simple trick is just to divide alpha star by m and use that as the significance level for each of our tests. Because if we do that, then our family-wise error rate is definitely not going to be higher than alpha star. And the equivalent procedure is to multiply all the p-values by m. And this adjustment is known as the Bonferroni correction, and it's probably the simplest and most widely used sort of multiple comparisons correction. And the beauty of it is that it works without any assumptions at all. It's just a feature of probability theory. So you don't need to assume anything about the distribution of the data or about whether things relate linearly or whether you're talking about means or medians. It doesn't matter what you do, Bonferroni will always protect you. The problem with it is that it's really conservative. So that bound, the FWER being less than or equal to m alpha, that could be a really loose bound. Often the family-wise error rate will be much less than that. And so if you control that, you could end up in a situation where you're just completely destroying your power. Because now you're setting such a high bar to declare something significant that you basically end up declaring nothing significant. So you're protected against one type of error, but you're completely sacrificing the other type of error. So because of this, people have sort of been interested in trying to do somewhat better than Bonferroni. And there's a simple trick, which is called Sidax method. And basically, what this does is it turns that inequality into an equality. And the way it does that is by assuming that all the tests are independent. Independent meaning that if I know whether a given test rejected or didn't reject the null, I don't know anything about whether the other tests rejected or didn't reject the null. So there's no information about one test that you can gather from another test. If that's true, then you can actually establish that equality at the top there, and then a simple inversion of the equation gives you this sort of formula for adjustment. And this method is more powerful than Bonferroni, so it doesn't kill your power as much, but it does require this assumption of independence, and that may not always be true. Often, if you're doing sort of batch testing and things like this, some of the tests may end up being sort of correlated, and sort of assuming they're independent can actually sort of lead you astray. So if you have good reason to believe they're independent, you can do sort of better with SIDAC, but you are sort of at the cost of making this additional assumption. So another class of methods is called step-down methods, and the two I just mentioned are called single-step methods, and they're called single-step because basically they just take an individual alpha or an individual p-value and just apply a simple transformation to it. The step-down methods apply different transformations to different p-values, and the idea is essentially that they get less aggressive the higher the p-value is in terms of their correction. So Holmes adjustment is sort of the most popular version of this. It's also sometimes known as Holm-Bonferroni. And you don't really need to interpret that expression too carefully, but the key point is that it's not applying the same multiplier to every p-value. What it's doing is it's sort of sorting the p-values, putting them in order, and then it's applying the Bonferroni factor to the smallest p-value, and then it's applying something slightly smaller than the Bonferroni factor to the next smallest p-value, and something smaller to the next smallest, and so on. And it turns out that this actually controls the family-wise error rate just as well as the Bonferroni does. But it also preserves your power a lot better. So if you look at this table, this is just some examples of, I have 8 genes, and the first column is sort of their individual p-values, and if we use sort of our nominal significance level of 0.05, we can see that 5 of the genes are statistically significant. If we do our Bonferroni correction, we just have to multiply them all by 8. For the ones that are bigger than 1/8, we just cap them off at 1. And so what Bonferroni does is it basically kills all but 2 of our genes, right? So we're losing 3 of the genes that were previously significant, but it is controlling the family-wise error rate. SIDAC actually also does just about the same as Bonferroni, though if you look at the p-values side by side, you can see that the p-values from SIDAC are generally a tiny bit smaller than the Bonferroni ones. So it is a bit more powerful, but in this case, it's not powerful enough to actually give us, more significant genes. Holm, by contrast, actually preserves 4 out of the 5 genes, and happens to control the family-wise error rate just as well as Bonferroni does. So step-down methods are generally sort of the preferred method when your goal is to control the family-wise error rate for this exact reason, that they do in fact control it, but they do a much better job of preserving power. Another method that's popular, especially in sort of the high throughput setting, is sort of Westphal and Young's method. I won't talk about that in detail, but essentially the advantage of that over the Holm procedure is it actually takes into account the correlations between all the tests. So Holm is just taking into account the ordering of the p-values, but it's ignoring how the tests are correlated with each other. But Westphal and Young actually exploits that in order to achieve even slightly more power than Holm. The last thing I'll talk about with the family-wise error rate methods is sort of permutation methods. And so, there's a very general way of doing hypothesis testing that extends in a natural way to dealing with multiple testing, and that's called permutation methods. And the way a permutation test works is you basically take your groups, so in our example, sort of cancer versus non-cancer, and you just scramble the labels. So you just randomly shuffle them. And the reason you can do this is because under the null hypothesis, there's no group difference. So when you shuffle the labels, you're eliminating whatever group difference there appears to be and getting a sense of what the data would look like under the null hypothesis. And you do this a large number of times, call it R times. And in each one, you calculate your test statistics. And then to control the type 1 error rate, you just use the tail probability, which will sort of tell you sort of how extreme the test statistic is. Now, when you're doing multiple tests, the only difference is you calculate all the test statistics under each of these permutations. And this gives you sort of the joint distribution of these statistics. and then you use sort of a joint tail probability to do the same thing. Now, how you do this mechanically is a little complicated. I don't want to spend too much time on it, but the point is, this is a completely flexible method, and it can basically be used, in any situation. It's completely assumption-free. It's also rather efficient in the power sense. The problem with it is that it's, you have to code it up yourself because it's very sort of scenario specific, and it can be computationally expensive. So if you have a large data set or a large number of genes, doing this exercise can take a lot of time, a lot of computing power. So generally, permutation methods tend to get saved for situations where people feel like methods like the home method are not up to the task, which are sort of fairly unusual situations. But in principle, you could use this essentially always. Now, often when we're doing a power calculation, we want to take into account the fact that we're actually going to be trying to control the family-wise error rate in the course of our analysis, which is usually not what we do when we do a power calculation. And the simplest way to do this is just use the Bonferroni method, because Bonferroni just means you're scaling the alpha by the number of tests. So that's a very simple trick. You can just adjust your alpha and do your power calculation and you're done. If you wanted to do something like the home method, you can do it, but it ends up being quite a bit harder to sort of figure this into your power calculation. And so typically, in order to do this, you need to do a simulation study, which is a bit of extra work. The other advantage of the Bonferroni is because it's conservative, you can sort of interpret it as a lower bound on the power. So the power you get from Bonferroni, you can sort of think of as, we're going to have at least this much power. And so if your power is really high, then it's great, and you don't care that it's too conservative. But if it's really low, then you might want to think about, okay, can we do this more carefully in a way that might show that we actually do have more power than Bonferroni suggests. Now, this is great, and you can do all of this, but at the end of the day, if you have a large number of tests, if M is really large, it really doesn't matter which of these methods you do. Your power is basically just going to be blown away. Think about a situation where you do 100,000 tests, right? Bonferroni is going to be dividing 0.05 by 100,000. And it's pretty hard to get p-values that are that small, especially if you don't have a massive sample size. So one trick you can do if you're insisting on controlling a family-wise error rate is to try to eliminate genes that you think have a low signal-to-noise ratio. So often when we have data in the form of read counts, for example, we'll throw out any markers where the read count is really low. And the reason is because we think that there's not enough variance in there in order to be able to be correlated with anything. So that would be sort of a case of low signal. In other cases, we throw out genes where we think the coefficient of variation is really high, and that's because we basically think that there's just so much noise that it's not even reproducible, that it's not going to be correlated with anything either. So you could have very little signal, or you could have too much noise. And if you throw out those genes, then you can sort of reduce n to some more manageable number. So you can go from 100,000 to like 10. And once you're down to 10, then getting 0.005 is not necessarily as difficult of a burden to clear as getting, 5 times 10 to the negative 6th or whatever. So that's a common trick that people will do. But, that can often be sort of disappointing because now you're not testing all these different genes that you collect the data on. And so the question often arises is why are we so worried about making even one type 1 error? Because that's really what the family-wise error rate is about. And so is there a different way we can think about the group error rate that is not so focused on just making one error, but about our general tendency to make errors? So that leads us to the false discovery rate, which is a different concept of multiple testing error. And this became really popular in the 90s when sort of high throughput data analysis started becoming a major feature of biological sciences. And the reason was because we were getting these absolutely massive data sets where there was a huge number of biomarkers to test, and in order to control family-wise error rate at any reasonable level, you would need millions of patients where you often had something like 40 or 50. So what researchers came up with was, instead of worrying about the family-wise error rate, you can control this thing called the false discovery rate. And what the false discovery rate is it's the expected proportion of rejected nulls where the null is actually true. So you do m tests, and of those m tests, you reject the null in some of them. And the question is, what proportion of those ones you rejected is the null actually true? Meaning you've made a discovery, but your discovery is actually false. And what's nice about this definition is, A, it really does capture, in some sense, the group error rate. It's telling you something about the tendency of you to make errors of this kind, but it doesn't automatically increase with the number of tests you're doing. So in the way that the family-wise error rate just sort of explodes when you do more tests, the false discovery rate doesn't actually automatically increase with the number of tests. And so you can do a huge number of tests and still potentially control the false discovery rate at a satisfactory level. It's important to note, though, that it's a sort of weak correction that you're doing. And one reason for this is that the actual proportion of false discoveries in your data set may exceed the expected proportion. So if you control the false discovery rate at 5%, you think, oh, only 5% of my things that I declared significance on are wrong. But in fact, in your particular data set, it may actually be 50%. It's just that on average across all data sets, it averages out to 5%. So it's a very weak form of control as compared with the family-wise error rate, which is guaranteeing you that you have a certain probability of making even one error. So, one reason people dislike the false discovery rate is because it's so forgiving in that way. But its forgivingness is sort of what makes it feasible for these sort of high throughput problems. Now, there's different procedures people use to control the false discovery rate, but the standard one is the Benjamini-Hochberg procedure. And this is a step-up procedure versus a step-down procedure that we mentioned before. And again, it sort of orders the p-values and sort of applies a sequential set of cutoffs to the p-values that are sort of varying by where you are in the order. So you sort of apply a more stringent threshold to the smallest p-values and increasingly less stringent ones as you move up the order. And it turns out that this pretty simple sort of check on these p-values actually controls the FDR at whatever your desired level is, alpha star, in this notation. And Benjamini-Hochberg sort of assumes that the tests are independent, but it actually works pretty well if you have certain types of dependence. But other types, sort of unusual patterns of dependence, it can perform sort of poorly in, and so there's a sort of generalization called Benjamini-Yekutieli, I'm not sure I pronounced that, which sort of expands Benjamini-Hochberg to deal with arbitrary dependence. I'm not going to spell that out here because the calculations are sort of more complex, but it turns out that in the case of independence, it just reduces to the Benjamini-Hochberg formula. So an important notion to think about here is Q-values, which are sort of analogous to P-values. So when we want to control the family-wise error rate, what we do is we take our P-values and we sort of correct them either by adjusting the p-values directly or we adjust the alpha level that we're comparing them to. And so the p-values sort of perform this function again, avoiding us committing to a type 1 and type 2 error trade-off. So analogously, when we're talking about the false discovery rate, a q-value is just sort of like p-value, and then it's sort of a quantity that we can compare with an FDR threshold, and we can let the user sort of decide what the FDR threshold is that they want to apply, rather than sort of saying, is it significant or not at some arbitrary level that we've chosen. So this also allows us to sort of avoid committing to a particular trade-off between sort of here not type 1 and type 2 error, but between false discovery rate and type 2 error. And definition of a q-value analogous to p-value is when you're doing m tests, it's the minimum FDR of those m tests at which the data reject the null. So the p-value was the minimum significance level at which the data reject the null, and so here it's the minimum FDR. And in order to get the q-values, you basically just do the opposite of the Benjamini-Hochberg procedure, which is sort of a procedure for deciding what is and isn't significant. You just sort of invert that to calculate these q-values. And if we go back to that example that I showed before and we add this q column on the right, what you can see is actually, in this one, it actually preserves all 5 that were originally significant. So we actually turn out not to lose anything here. Though you'll notice that the q-values are all bigger than the p-values. So it is doing an adjustment. It is sort of penalizing them for having done multiple testing, but it turns out that it penalizes them in such a way that we don't actually lose any power. But what's important is when we were comparing, say, Home and Bonferroni, both of those were controlling the family-wise error rate. It's just that Home was strictly better because it's more powerful. When you compare Home and the q-value, that's not such a fair comparison, because while q-value is more powerful, it's controlling a weaker notion of multiple testing error, right? It's controlling the false discovery rate, whereas Home is controlling the family-wise error rate. So in this case, I would actually argue that the Home may be the more persuasive thing to use because you're not actually sacrificing power that much and you're controlling a more rigorous notion. but that's only because we're doing 8 tests. If we were doing 100,000 tests, you would probably see a big advantage of using the Q values. So that's sort of why in the sort of high throughput setting, the Q values and sort of false discovery rates turn out to be the preferred method in many cases. And if we want to do power analysis where we control for FDR, like how we did for the controlling the FWER, instead of doing a Bonferroni correction, we can use this formula that just is a consequence of Bayes' theorem. Basically, it turns out the FDR depends on sort of 3 numbers. 1 is sort of the type 1 error rate of each test, the significance level. 2 is the power, or the type 2 error rate of each test. And 3 is an interesting quantity. It's sometimes called the prior probability in a Bayesian context, but in a more general sense, what it is it's sort of what proportion of the tests we're performing do we actually think are real signals. So we test 100,000 genes, but maybe we only think 10 to 20% of those are actually differentially expressed between cancers and non-cancers, right? And so pi is sort of, it's a hard number to actually know unless you have, like, say, a meta-analysis of exactly the topic that you're studying that you can refer to. But generally, you know, what this is it's sort of your sense of what the signal rate is among the tests that you're performing. Now, what's cool about this formula is it shows very clearly that the FDR does not depend on M. So this is sort of what I was saying about how the FDR does not automatically grow with the number of tests you're doing. The other nice thing about it is you can use it to adjust your power calculations. So if what we want is 80% power, and we want to control the FDR at 5%, and as I said, we think that our signal rate is something like 10 to 20%, then we can use this formula to derive an adjusted alpha. And the goal here is not adjusting alpha, again, to control the family-wise error rate like before. It's just figuring out what alpha would induce the appropriate false discovery rate, which is what we actually care about. And so once we have those 2 alphas corresponding to 10 to 20%, we can then do, say, what's the minimally detectable effect size using that alpha. And that would be sort of how we would adjust our power calculation for false discovery rate control. And this is just a visualization of these factors that go into determining the FDR. So on the y-axis is the FDR, and on the x-axis is that prior probability or the signal rate. And the different curves correspond to different amounts of power. And this is all sort of using an alpha of 0.05. So what you can sort of see is that when the signal rate is high, the false discovery rate goes down. And going the other way, when the signal rate gets low, the false discovery rate sort of explodes. So if you do 100,000 tests, but you only think that 1% of them are signals, you're going to have a very high false discovery rate pretty much no matter how much power you have. And that's just because you're basically trying to find needles in a haystack. Whereas on the far right, you're basically everything's a needle. And so you don't have to look too hard. And so even when you have really low power, you can actually control the false discovery rate at a pretty low level. But in general, increasing your power will reduce your false discovery rate. But you can see that the effect of that is quite swamped by the signal rate. And so the signal rate is a really important sort of underlying factor in thinking about what the FDR is. So if you're familiar with R, and I think R is sort of the preferred language for doing sort of a lot of high throughput analysis. There's a very simple function that comes in base R that you can use to do some of these corrections. It's called p.adjust. And what I've written here is just sort of listed out the p-values from that table I showed in a vector, sort of using that concatenation operator, C, and then I just stick each one into p.adjust and just tell it which adjustment to do. So I can tell it to do a Bonferroni, I can tell it to do a home, I can tell it to do a false discovery rate, and that just spits out the numbers that I showed you in the table before. So the nice thing about this is you don't need to integrate this into your analytic workflow. All you need to do is do the analysis you were going to do anyway, and then at the end of the day, just collect all your p-values and stick them in here. There are more complicated methods that require you to actually feed in the data. Those typically are reliant on the model in some way. So like two-piece correction, for example, is sort of using information in the model. And so you need to, in the course of model fitting, sort of build in the type of correction that you're going to be doing. But for these methods that we talked about today, these are all non-parametric methods. And so all they do is they just take the list of p-values and do the calculation. So it turns out that while this is a really important thing to do, and it's increasingly important that people do it, it turns out it's actually really trivial to do. And so, you can sort of think of this as sort of the last step in your analysis, is just sticking this stuff into R and getting the, either the adjusted p-values or the q-values in the case of the FDR. So to summarize, the useful thing about p-values is that they do provide type 1 error rate control, but they do so only for individual tests. They don't really give you any control over groups of tests. And in general, when you have large groups of tests, they'll become increasingly irrelevant. And in high throughput problems, multiple testing is really central to the enterprise. And then we have lots and lots of features, and we want to see how many of these features are differentiated between the groups that we care about. And what we've seen from the reproducibility crisis is that there's a lot of attention being paid to the actual error rates of research, and the actual error rates really reflect more the group error rates and not just the individual error rates. And so there's two concepts of these group error rates that you want to think about. The family-wise error rate is sort of the ideal one, but it's very conservative. And so you're able to feel comfortable that you're controlling your errors, but you're also probably throwing out tons of gold in the process. The false discovery rate is a lot more forgiving and it's a lot more appropriate for high throughput settings, but it's important to understand that it's a weak sort of control, and that in any given data set, you may actually have quite a high error rate, even if you've exerted some level of false discovery control. And so that's all I have. Any questions?
I have a question. So, for example, if we have a data set, we have a bunch of genes. We have gene expression data. We also have protein data. So we have a bunch of p-values for the gene expression data. We also have tons of p-values for the protein expression data. When you adjust for the p-value of FD, how do you, which is your set? You know what I mean?
This is a really good question, and this is, I think, sort of the dark arts of multiple comparisons adjustment, which is, what exactly do you combine into your group of tests that you adjust for?
And also, like, if the investigator want to try different models, how do you group the p-values to adjust this?
Yeah, this is, I think, unfortunately, there isn't really a good answer to this.
Okay.
I think
this has always been in my
so I think there's a philosophical answer to this, which is that you need to think about which tests are pertain to which scientific hypotheses. So you have a set of scientific hypotheses, and maybe your gene expression data bears on hypothesis 1, and your protein data bears on hypothesis 2. Alternatively, maybe they both bear on hypothesis 1. Maybe hypothesis 1 is just something's going on here, right? And if that's the case, then you really want to combine them together. If they're separate hypotheses, you want to sort of think about them separately, because you want to sort of control the per hypothesis error rate. That's sort of the philosophical answer. The real world answer is it's whatever the journal reviewer wants you to do. And this is, I've had, journal reviewers who want me to lump every single p-value in the paper, regardless of how disconnected they are, into a correction. I've had other ones who've said, we want sort of a correction for these analyses and a correction for these analyses. Often you can sort of persuade them a bit if you sort of reason about how differentiated conceptually certain things are. But in general, what I would say is that when you lump everything together, you're going to get the most conservative answer. Yes. And so if you have a really strong set of signals in your paper, then I would just do that, because it makes your paper look really good. It's like I did the most aggressive type of correction, and all my stuff, stood out. If you can't do that, then what I would do is sort of adjust it within natural groupings. Like table 2 is all about this, our primary outcome, and so we'll do an analysis just for the primary outcome, and then table 3 is all about the secondary outcome, and so we're all going to do it, And then just state that what you did is you controlled, say, the false discovery rate per outcome. Yeah. And that's just a disclosure thing. You want the reader to understand what you actually did, so that they can then say, okay, you did do some correction, but it was a fairly weak type of correction. Or you did a really strong type of correction, and wow, everything sort of shut up. But if you always do the strongest form of correction, you're often going to basically obliterate your power, and you're not going to find anything. And so you don't always want to do that. But I think the key thing here is to be transparent about what you did, and to sort of be explicit about what your sort of conceptualization of the problem is, so that it's clear why you grouped certain things and not other things. All right, well, I guess that's it. Thank you for having me.